According to the National Electrical Code, Section 250.52 FR, grounding electrodes shall be installed so as to minimize the impedance of the grounding path. Section 250.52 FIF states grounding electrodes shall be listed and installed in accordance with the requirements for this specific type. Section 250.52 C2 details concrete encased electrodes, stipulating they shall be not less than 20 feet in length, shall be at least 0.625 inches in diameter, and shall be embedded in at least 2 inches of concrete, extend at least 1 foot into the earth, and have a total embedded and exposed length of not less than 8 feet. Based on the provided information, the rods in question do not qualify as concrete encased electrodes as defined by the National Electrical Code. The rods are only 8 feet long, falling short of the required 20 feet for concrete encased electrodes. Moreover, the rods are not fully embedded in the soil, with only 6 feet of their length in contact with the earth. Consequently, the installation does not align with the stipulations outlined in the National Electrical Code. The inspector's correction is deemed valid. The rods do not meet the minimum requirements for a grounding electrode, and the concrete patch does not compensate for the lack of concrete encasement. It is possible to argue based on the conductive value of concrete. However, the inspector's interpretation of the code holds merit. To pass inspection, grounding electrodes must meet the requirements of the National Electrical Code. This can be achieved by installing either 2 concrete encased electrodes, each at least 20 feet long and embedded in at least 2 inches of concrete, or 1 rod electrode, at least 8 feet long and driven fully into the earth. To further elaborate, the purpose of a grounding electrode system is to provide a low impedance path for fault current to return to the source, which in turn facilitates the operation of overcurrent protection devices such as circuit breakers or fuses. This is a critical safety measure designed to protect people and equipment from electrical shock and fire hazards. The National Electrical Code sets specific requirements for grounding electrodes to ensure their effectiveness in achieving this purpose. Firstly, let's discuss the concrete encased electrode, often referred to as a U for ground. This type of electrode is described in Section 250.52 C2 of the National Electrical Code. It must be at least 20 feet long and consist of either a 0.625 inch or larger diameter reinforcing bar or a number 4 or larger bare copper conductor. This electrode must be encased in at least 2 inches of concrete and located within the concrete foundation or footing. The code specifies these dimensions and materials to ensure that the electrode has sufficient surface area in contact with the concrete and earth to provide a low impedance grounding path. The 20-foot length is crucial because it maximizes the contact area between the electrode, the concrete, and the surrounding earth, thereby reducing the resistance of the grounding path. The 2-inch concrete encasement is necessary to protect the electrode from corrosion and to maintain good electrical contact between the electrode and the concrete. Now let's examine rod electrodes, which are covered in Section 250.53G of the National Electrical Code. A rod electrode must be at least 8 feet long and made of either steel or copper. It must be driven into the ground so that at least 8 feet of its length is in contact with the soil. If rock bottom or similar conditions prevent driving the rod to its full length, it can be buried in a trench that is at least 30 inches deep. The purpose of the 8-foot minimum length is to ensure that the rod is in contact with a sufficient volume of soil to provide a low impedance grounding path. The depth of burial is also important because the soil at greater depths tends to be more moist and conductive than the soil nearer the surface. In the scenario described, the inspector cited a violation because the grounding rods were not installed in accordance with the National Electrical Code requirements for either concrete encased electrodes or rod electrodes. The rods were only 8 feet long, which does not meet the 20-foot minimum length for concrete encased electrodes. Additionally, they were not fully embedded in the soil as required for rod electrodes. The argument that the concrete patch compensates for the lack of proper installation is unlikely to be accepted by the inspector. While concrete does have some conductive properties, it does not provide the same level of grounding performance as a properly installed concrete encased electrode or rod electrode. The National Electrical Code is very specific about the requirements for grounding electrodes, and inspectors are generally required to enforce these requirements strictly. To resolve the issue, you have a few options. Firstly, you could install 2 concrete encased electrodes that meet the requirements of section 250.52C2. This would involve embedding 20-foot-long reinforcing bars or bare copper conductors in the concrete foundation or footing. Secondly, you could drive a rod electrode into the ground so that at least 8 feet of its length is in contact with the soil. If you encounter rock bottom or similar conditions, you can bury the rod in a trench that is at least 30 inches deep. Thirdly, you could use a combination of grounding electrodes such as a rod electrode and a ground ring. A ground ring is a bare copper conductor that is buried in the earth in a circular or U-shaped configuration. The National Electrical Code allows for the use of multiple grounding electrodes to improve grounding performance. When installing grounding electrodes, it is important to follow all of the National Electrical Code requirements carefully. This includes using the correct materials, installing the electrodes at the proper depth and spacing, and making sure that all connections are tight and corrosion resistant. It is also important to have your work inspected by a qualified electrical inspector to ensure that it meets the code requirements. Grounding electrode systems play a critical role in electrical safety. By providing a low impedance path for fault current to return to the source, they help to protect people and equipment from electrical shock and fire hazards. Therefore, it is essential to install grounding electrodes correctly and to maintain them in good condition. The installation in question does not meet the minimum requirements for a grounding electrode as defined by the National Electrical Code, specifically section 250.52. The grounding electrodes used are not long enough to qualify as concrete encased electrodes, nor are they installed correctly as ground rods. The code requires a minimum length of 20 feet for concrete encased electrodes, and these electrodes do not meet the requirement. Additionally, ground rods must be driven into the earth to a depth of at least 8 feet, and the described installation does not meet this requirement either. The assertion that the concrete patch improves conductivity and compensates for the improper installation is not supported by the code. While concrete can conduct electricity, it does not provide the same level of grounding as a properly installed electrode. Therefore, the inspector's call is likely correct, and the installation would need to be corrected to meet code requirements. To meet code requirements and resolve the issue, there are several options. One option is to install concrete encased electrodes that meet the 20-foot minimum length requirement. This would involve encasing a 20-foot length of reinforcing bar or approved conductor in concrete. Another option is to drive ground rods into the earth to a depth of at least 8 feet. If rock or other obstructions prevent driving the rods to the required depth, they can be buried horizontally in a trench that is at least 30 inches deep. It's important to note that the National Electrical Code does not recognize a partially driven ground rod as meeting the requirements for a grounding electrode. The code is very specific about the installation requirements for grounding electrodes, and these requirements must be followed to ensure the safety and effectiveness of the grounding system. In addition to the length and installation depth requirements, the National Electrical Code also specifies the size and type of conductor that must be used to connect the grounding electrodes to the electrical system. The grounding electrode conductor must be sized according to the size of the service entrance conductors, and it must be made of copper or other approved material. The grounding electrode conductor must be securely connected to the grounding electrodes and to the service equipment. It is important to consult the National Electrical Code for specific requirements related to grounding electrode conductors. Furthermore, it's worthwhile to consider the function of grounding and bonding in an electrical system. Grounding is the intentional connection of a neutral conductor or equipment enclosure to earth. Bonding is the connection of metallic parts to form an electrically conductive path that ensures electrical continuity and the capacity to conduct safely any fault current likely to be imposed. The purpose of grounding is to provide a low impedance path for fault current to return to the source, thereby tripping a circuit breaker or fuse and energizing the circuit. The purpose of bonding is to minimize voltage differences between metallic parts, thereby reducing the risk of electric shock. The grounding electrode system is a critical component of the overall grounding and bonding system. It provides a connection to earth that helps to stabilize the voltage of the electrical system and provides a path for fault current to flow. A properly installed and maintained grounding electrode system is essential for electrical safety. In conclusion, the grounding rod installation, as described, does not meet the requirements of the National Electrical Code, and the inspector's call is likely correct. To resolve the issue, you would need to install grounding electrodes that meet the code requirements, such as concrete encased electrodes or ground rods driven to the proper depth. It is also important to ensure that the grounding electrode conductor is properly sized and connected. Consulting the National Electrical Code and working with a qualified electrician are essential for ensuring that the grounding system is installed correctly and safely. The resistance to ground is also an important factor to consider. While the National Electrical Code does not specify a maximum resistance to ground for a single grounding electrode, it does require that the resistance to ground be low enough to ensure that the overcurrent protection devices will operate properly in the event of a fault. In many jurisdictions, a resistance to ground of 25 ohms or less is considered acceptable. If the resistance to ground of a single grounding electrode is greater than 25 ohms, an additional grounding electrode may be required. The resistance to ground can be measured using a ground resistance tester. This instrument applies a small current to the grounding electrode and measures the voltage drop to determine the resistance. It is important to use a calibrated ground resistance tester and to follow the manufacturer's instructions carefully. The soil conditions can also affect the resistance to ground. Soil that is dry or sandy tends to have a higher resistance than soil that is moist or clay. The presence of rocks or other obstructions in the soil can also increase the resistance to ground. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or to treat the soil to reduce its resistance. Soil treatment can involve adding chemicals to the soil to increase its conductivity or by replacing the soil with a more conductive material. Another consideration is the location of the grounding electrodes. The National Electrical Code requires that grounding electrodes be located as close as practicable to the service equipment. This minimizes the length of the grounding electrode conductor and reduces the impedance of the grounding path. The grounding electrodes should also be located in an area where they are protected from physical damage. They should not be located in an area where they are likely to be disturbed by digging or other activities. Grounding electrodes should also be accessible for inspection and testing. It should be possible to measure the resistance to ground without having to dig up the electrodes. Regular inspection and testing of the grounding system are important for ensuring that it is functioning properly. The grounding electrodes and grounding electrode conductor should be visually inspected for signs of corrosion or damage. The resistance to ground should be measured periodically to verify that it is within acceptable limits. Any problems with the grounding system should be corrected promptly. In addition to the grounding electrodes, the grounding electrode conductor, and the resistance to ground, there are other important aspects of the grounding system to consider. These include the bonding of metallic water pipes, gas pipes, and other metallic objects that may be present in the building. Bonding is the connection of these metallic objects to the grounding system to ensure that they are at the same electrical potential. This reduces the risk of electric shock in the event of a fault. The National Electrical Code has specific requirements for bonding metallic water pipes, gas pipes, and other metallic objects. These requirements must be followed carefully to ensure the safety of the electrical system. Surge protection is another important consideration. Surge protection devices, or SPDs, are designed to protect electronic equipment from voltage surges caused by lightning, power line disturbances, or other sources. SPD are typically installed at the service entrance and at other locations throughout the building. The National Electrical Code has requirements for the installation of SPD. These requirements must be followed carefully to ensure that the SPD will function properly in the event of a surge. Finally, it is important to remember that the grounding system is only one part of the overall electrical safety system. Other important components of the electrical safety system include overcurrent protection devices such as circuit breakers and fuses, ground fault circuit interrupters, or GFCIs, and arc fault circuit interrupters, or SIs. These devices are designed to protect people and equipment from electrical shock and fire hazards. It is important to ensure that these devices are properly installed and maintained. In summary, the grounding system is a critical component of the electrical system that is designed to protect people and equipment from electrical shock and fire hazards. The National Electrical Code has specific requirements for the installation of grounding electrodes, grounding electrode conductors, bonding conductors, surge protection devices, and other components of the grounding system. It is important to follow these requirements carefully to ensure the safety of the electrical system. Regular inspection and testing of the grounding system are also important for ensuring that it is functioning properly. If you have any questions about the grounding system or any other aspect of the electrical system, you should consult with a qualified electrician. They can help you to ensure that your electrical system is safe and code compliant.